Oh, I do have some good news. So with all of the bad things in the world right now, here's a big positive. I got the 1000 CFM stove vent fan installed on Friday for cooking my steaks without smoking up the whole house, because I like to blacken them. So my test run was I basically lit a ribeye steak on fire in a cast iron pan, and I just had it on high heat the whole time, and it was just charring, smoking, zero smoke in the house. The guys were a little bit hesitant to install it at first because they felt like they needed to warn me that something that moves that much air could actually drain the oxygen from the house. So they suggested I not run it at the same time as the fan on my my fireplace. I have two fireplaces on the main level, and he says, you know, don't run the fan on the fireplace at the same time, because you'll end up evacuating your house of oxygen and everybody will die. So that is the type of exhaust you should have. Okay, so let's look at what the homework was. So we're creating a program outside of Box. So we're looking at just file IO or file systems, right? So we're going to implement a file manager in C that could be used by an OS. We would need to integrate it into our blah, blah, blah. So create a programmatic representation for a hard drive that has sector and file manager that abstracts those sectors into blocks. Which means we need a representation for blocks. So we'll think about how we want to represent those things. We're going to create a data structure for the file allocation table, as well as a directory allocation table. I mentioned on here, this can be pretty simple, because we just need to know the first block of each file, and we're not going that much depth with different volumes and stuff. So next, create a simulation that allows the user to store a bunch of the files of a given size on the hard drive and show the contents of the file allocation table, as well as the directory table, which should be a bunch of base addresses effectively in the directory table. So we're going in the direction of blocking the data, turning them into blocks as a collection. Okay. So for instance, if our program asked you how many bytes is your file, and we said 25,000 bytes, this would then create 49 sectors that would be filled up with, that would ultimately fill up 7 blocks. And it would show a file allocation table with the directory table having just the starting block for that. So if we go back and review what we talked about last time, we were talking about the idea. So we're in this world right here, right? So this piece right here, and then our directory table. So we have a hard drive, and we want to be able to manage stuff on the hard drive. So this hard drive is kind of like an array of sectors, right? All right, we can think of it like an array of sectors. So on a hard drive, we have a bunch of sectors. So a sector is going to look like this. And by our example here, we're using 512 byte sectors. So we talked last time that a default for modern hard drives, if we're sticking with hard drive type things, not floppy disks or ATA things like CD-ROMs and DVD drives and stuff like that, but a standard is kind of that a sector on a drive is 512 bytes. So we can think of a hard drive as being a collection of sectors, where a sector has a bucket number and that it holds some bytes. All right, so we can kind of think of a sector as having an array of bytes. Does that make sense? All right, and then what we have is we have an abstraction that sits above the idea of a sector. These are called blocks. All right, where each block holds a collection of some sectors. So 6 there. So this is 8. So in our example here, we have a block that holds 8 sectors. And did I specify what we should, yeah, so a block is a collection of 8 sectors, each sector being 512 bytes. So that's what a block is, all right? So this guy holds a bunch of sectors, where a sector holds a bunch of bytes. Make sense? So far so good. I'm trying to talk this out in terms of the programming language structure stuff we're gonna have to create for this, all right? And then ultimately, we're going to have our directory format table that's going to keep track of the first position of these blocks, because when we take a file that is a collection of bytes and store it into a bunch of sectors and then block those sectors into a bunch of blocks that are going to be a multiple of 8 with some internal fragmentation for the last block, we get some stuff. All right, so let's start from the ground up. We're going to think of a single sector as being a collection of 512 bytes. Okay, so let me go over here. I did start the recording, didn't I? Yep. All right, so let's go into 450, and we're going to call, I'm going to create a new folder here. And we're going to call this guy file. We're going to call this guy file allocation simulator. All right. So that's the guy we will create there. We'll go ahead and create a new file, and we'll call this guy main.c. All right, and we'll just make sure everything is building the way it should be building. Let's see, we're doing C, so we're IO, standard IO. Standard IO.h, void main. Actually, we're doing standard C, so we'll say int C char pointer arg v, and we'll just do a print f hello world \n on it, and we'll return 0. Everything went to plan. All right, so let's go test this dude. All right, so we have GCC main.c, and there's our hello world. So we have a working deal here. Okay, do we have any suggestions on how we might represent a sector? Just like I have highlighted there, a single sector. Keeping in mind that all of us in here have gone through several programming classes, including data structures, and we should be thinking about these things in terms of data structures. So let's see where our minds went with this. How do I represent a sector? It's not rhetorical.
As an array of numbers?
Array of numbers, okay. How big's the array?
Wouldn't it be 8? Because there's 8 sectors in a block.
That's how we would represent a block. I'm not at this level yet. I'm just at this level right here. How do I represent that?
Well, you could do an array of 64-bit integers until you have a total of 512 bytes as your total array size.
What's the advantage of that? Why not just have 512 bytes?
Well, we don't have a 512-byte data type.
We have a 1-byte data type?
We do.
What's it called?
Char, or
Char.
unit 8_t.
Do we have a way of having a collection of 512 of those? What's that? An array. All right. So what I'm going to do for our, what do they call a sector? A sector is going to be a struct. All right, we've already seen structs, but you probably haven't written a whole lot of them yourself, right? What is a struct in C? What does it stand for? Structure, as in data structure. All right, so this is our precursor to objects in modern languages. So a struct is kind of like a, you can think of it like a Python dictionary. Name value pairs. All right, so maybe we have a struct called sector, and this guy has a int bucket ID or bucket number, and it also has a char array 512. And then we might want to also have a thing like int byte count. Because our, and actually we could even say we're not going to store the bucket number, instead we're going to store the byte count, because the bucket number is actually going to be managed by the, well, yeah, the bucket number will be managed by the hard drive struct we create, which will have a collection of sectors. So if I say that we have a 1 gigabyte hard drive, that means we have 1,024 megabytes times 1,024 is kilobytes times 1,024 is bytes divided by 512. That is a 2 billion sector hard drive, right? So we can hold 2 million rather. So this is a 1 billion byte hard drive is a gigabyte. And if I divide that by 512, which is the number of bytes that fit into a single sector, that gets me a 2 million sector hard drive. So a hard drive, our representation of a hard drive would be an array of 2 million sectors, where a sector is an array of bytes, as well as maybe the current byte count that fills it in a sector. When we divide up a file, that very last sector of that file is not going to be completely filled, right? Unless we get lucky. You know, you roll the dice and it happens to be indivisible by 512, then you have no internal fragmentation, but chances are, you know, high that you're going to have internal fragmentation. So a sector is going to be a, in fact, actually, I'm going to steal this. We'll put it on a separate slide too. So this is how we're going to represent a sector. So then we can similarly kind of talk about our solution being, we have a sector struct. We then have a hard drive struct. Our hard drive struct is a struct sector array of however big our hard drive is in terms of total sectors. So there's a 1 gigabyte hard drive-ish. I rounded to 1 million. It is 1 million, right? Yeah, it's 1 million. All right, so, you know, if I have my hard drive, that can be a sector array. And inside that array, we have bytes and we have chars. And we can also then have maybe a count in here of how many of our sectors are currently being used. So we might call this guy sector. It'd be called free sectors. So it's called total sectors, free sectors, used sectors. Maybe it's overkill keeping track of all three, but they're all related to each other. But given the fact that arrays in C don't know how long they are, total sectors is going to be kind of a an important value. Okay, but for our hard drive is effectively going to be a wrapper around a sector array, where a sector is a struct that holds a byte count and an array of chars, which is the actual data bytes. All right, then our block is going to be a struct, maybe called block, and this guy is going to hold, go back here, what is a block? A block is a collection of exactly 8 sectors. Make sense? That's what a block is. So we have, if we have a sector count in here as well. And then we have a struct sector array of size 8. That's what a block is. It holds 8 sectors, and maybe we keep track of the number of used sectors when we load a block. Because if you have a file that is less than, 512 times 8, actually let's do it times 7. If you have a file that is less than 3583 bytes, it actually won't even use the last sector of the block, right? The last sector of the block will be empty. We won't have any place to fill. So we're thinking about how are we abstracting our hard drive here. Our hard drive is abstracted this way. We have a hard drive, which is a collection of blocks. This is how the file system uses this. So this is how a file allocation table-based file system uses it. It's a FAT-based file system. So it says, okay, we have this idea of something called a block. Blocks are collections of 8 sectors, where a sector is a collection of 512 bytes. So my smallest thing I can access on an individual hard drive using a file allocation table is a block. So that means if I go to store something in a block can hold 512 times 8. So it can hold 4096 bytes, okay, or 4 kilobytes. A single block can hold 4 kilobytes, but that is our atomic level for hard drives. If I can't, if what I want to store doesn't take up 4 kilobytes, I'm going to have wasted space inside of a block, which will translate into wasted space inside of one or more of the 8 sectors that live inside the block. So I have multiple levels of internal fragmentation, right? So if I try to store a 1 byte file, as if that exists, but let's just say it does. If I try to store a 1 byte file inside of a block, I will have wasted 4,095 of the bytes that live in there. Or I will have wasted the entirety of 7 sectors, as well as almost the entirety of the 8th sector, because I only used 1 of the 512 bytes that lived in that 8th sector. All right, so we use that as an example. We call this the ultimate waste. Ultimate fat waste. It's a funny slide. The ultimate fat waste is assume a 1 byte file stored, assume a 1 byte file that we try to store in a file system. When we block the file, it comfortably fits within a single block, which is a collection of 8 sectors, each of which can hold 512 bytes, of which we will only use 1 byte from the very first sector. This will waste 511 bytes from sector 0, and will waste 512 bytes from each of sector 1 through 7. Total waste is 4095 bytes of internal fragmentation across the 8 sectors inside the 1 block. All right, so that would be the ultimate file allocation table wastefulness, is if we tried to store the smallest possible file. We're just saying it's 1 byte. I actually, realistically, you can't have a file that small when you think about a true file system, because files themselves, the data structure that is a file, will have to store more information, like for instance, read, write, permissions, things like that, than 1 byte. So this is an extreme, unrealistic example, but it at least exaggerates the idea of how we could be wasteful. Now, this is all because we have a way of taking our hard drive of sectors, abstracting it into this idea of a collection of blocks. Why do we do that? Why do we use a collection of blocks to abstract the number of sectors in our hard drive? What does that allow us to do?
You can like
Why not
use a
just
larger hard drive.
Yeah, have bigger hard drives. That's it. Okay. Otherwise, we can only have enough sectors to as high as we can count with the number of bits we use to index the array for our sectors in our hard drive. Okay, so if we use the 32-bit number, that means we can only have 2 to the 32nd, which is 4.1 billion, 4.3 billion, whatever, total blocks, or total sectors rather. And if each of those is a 512 bytes, that means our maximum size hard drive would be that 1024 is kilobytes, divided by 1024 is megabytes, divided by 1024 is gigabytes. So you can only have a 2 terabyte hard drive maximum size if you operated with a 32-bit number to count the buckets of your sectors with 512 byte sectors. So we're bypassing that limitation now. So we abstract it and give ourselves collections of blocks which hold groups of sectors underneath it. All right, and we've decided here this is how we're going to kind of lay this guy out. All right. So go back over here. Let's start writing some stuff with let's see what's running on my computer real quick. Something, the fan just kicked up. Is it just the VM? Oh, whatever. Okay, so what we're going to do is we're going to look at a struct. So I'm going to go ahead up here and I'm going to create a struct called a, what did I call it, a sector? And my sector struct is going to be, we decided a sector is going to hold on to a byte count and a char array of 512. So we'll have a int byte count, that's the number of bytes that live inside of a sector. Now we actually know that number to be exactly 512, right? So actually, isn't an int wasteful? If we're really thinking about memory here. So we could use a short to hold that, which is a 16-bit signed. I don't think bytes exist. So we use char for that. So that would give us, if we used an unsigned char, we could hold 512. No, we couldn't. 2 to the 8th is 256, right? Yep. So the smallest thing we could use is a short. Realistically, I'd probably just create an int, but if we wanted to, you could use the short, because that will hold a value between negative 32,768 and positive 32,767, which comfortably holds our 512 number. All right. And then our, and actually we can, if we want, we can say, I know it's not going to need to hold a negative number. So really we would use an unsigned short. And again, this is fluff. This is like, because we're 450 operating system students, you know, we really like to think about efficiency and things like that. You know, the modern programmer just slaps an int in front of this guy and moves on with life. All right. But we'll say this is an unsigned short because we don't need to hold negative numbers in the byte count. The worst it's going to be is we're holding 0 bytes inside of a sector. Biggest the number can possibly be is 512 bytes that we're holding in a sector. So this value only needs to be able to hold numbers between 0 and 512. Okay.
Out of curiosity, would we maybe
unmute
want
yourself,
to?
Appel. Thought you were. Were you talking, Appel? If you were trying to talk, you're muted.
I am unmuted on my side.
Unmuted.
All right.
Oh, you're listed as unmuted, but I don't hear you. Somebody else talk. Make sure I can hear.
I can hear him just fine.
Oh, I can't hear you either. Give me a moment. I heard people earlier, didn't I?
Yes.
All right, try now.
This is bad.
Oh, there we go. Now I can hear you.
All right. Out of curiosity, would we maybe want to have it signed so we could store negative numbers if there's an error?
Yeah, you could take this as far as you want, sure. But if we want to make our solution as cleanly understandable by a modern programmer, let's just throw an int on front of it and move on with life. All right, because this is, again, about abstraction. Okay, so we have our int byte count, and then we want to have our array of chars. So we're going to have our char, and we'll call this guy bytes. And there's 512 of those. Okay, so a sector will be one of these guys with 512 bytes. Then we decided that we would have something called a hard drive, where a hard drive would have some free sectors, total sectors, used sectors, and then an array of sectors. So we have our struct, call this guy HDD. And this guy will have, what all did I say? So total sectors, used sectors, free sectors. Total sectors, used sectors, free sectors. and then our array of sectors. So this will be a struct sector. We'll call this guy sectors. Let's see. Since I don't know how many sectors are going to be in this guy, we're going to actually do this as a struct sector pointer called sectors. It'll point to that memory when we create that memory. Okay. Then for our block, we're going to have a, this is used sectors. And then a array of 8 structs sectors. So struct block will be a array called used sectors, and then we'll have a struct sector sectors of size 8. All right, so those are our 3 structs that we're going to use to play our little game here, right? Our simulation. All right, now we want to actually have a couple of functions that allow us to build these guys. All right, so when we first fill up create a sector, maybe we have this guy sets all the bytes to 0, something like that. Realistically, actually, I think we can default this anyways. So I'll set byte count. I can't default it to 0. That's sad. All right, so we'll just create some functions. So we'll have a function that returns a struct sector called gen sector. This will get us a sector, and what we'll do is we'll create a struct sector temp dot byte count will start off as 0. Now really we could spin through our byte array here and fill it up with zeros, but it's already going to be filled up with zeros. Doesn't really matter because we've already marked that we don't have any used bytes in there. So we're going to say this is good enough. So we'll just return our temp. So this guy is effectively a constructor for a sector. So we're starting to see here how we're basically doing object-orientedness through the use of a non-object-oriented language. All right, so I have my my get sector there, or I actually meant this to be gen sector. I'm generating a sector, and he will create a brand new struct, set its byte count to 0, and then return that struct. That's what he does. All right, if we want to test this real quick, we'll go ahead and say struct s, or struct sector s is equal to gen sector, and then we'll go ahead and we'll print out the number of bytes is %d s dot byte count. Save that. Number of bytes is 0, and if we want to prove to ourselves that that was a real thing, we'll just make it 13 here, run it again, and you'll see it's not the default value. There's our 13. All right, so this guy created a physical struct for me. And remember, in C, structs are passed by value. So this guy created a physical struct for me, just like an int, and then I returned that struct. I stored it here in this this value. Okay. Now we need to have a constructor for, well, we can have a gen hard drive next. So our constructor for a hard drive, struct HDD gen HDD, and maybe this guy's going to take in a size in, what do you want? Bytes? Somebody byte hard drive? Let's take it in, what, well, let's keep it simple. We're going to take it in as bytes. Okay, so we have our gen hard drive, and actually what we can do is we can say, give it to me in a number of sectors if you want. So number of bytes is going to be a number of sectors. Typically, the presumed thing here is bytes must be a multiple of 512. You know, if you're a hard drive builder and somebody's asking you to build a hard drive, and your sectors, the little memory modules you have called a sector, only holds 512 bytes, the number of sectors you're going to put in a hard drive is going to be a multiple of 512. So you don't have to put in like a 13% of a sector in there or something like that. All right, so we can assume bytes is a multiple of 512. All right, so how many sectors are we going to need in this hard drive? Remember, our hard drive here is going to take in a total number of sectors, the number of used sectors, the number of free sectors, and then it's going to have a pointer to your collection of sectors. So we'll go ahead and create a struct HDD, call that guy temp. Then we'll have temp dot total sectors is equal to bytes divided by 512, which we'll assume is the number of bytes or number of sectors. If it's not, we'll just truncate, because that's what integer division does. Temp dot free sectors is going to be the same as temp dot total sectors initially. Temp.use sectors is going to be equal to 0. We aren't using any of the sectors yet. All right, but now we need to go ahead and generate an array that is enough, can hold enough bytes to store our sectors. And I don't think it's going to let me, I think I need to allocate the memory directly for it. So set in standard lib. Malloc standard lib.
I do have a question that's maybe a bit off topic,
Okay.
but if a hard drive is made as a multiple of sectors, then if the total number of sectors is, let's say, a multiple of 9, and you have 8 sector size blocks, are you going to have a gimpy little block at the end that just has, you know, one lone sector because you couldn't fit it all evenly into multiples of 8?
Keep in mind, blocks are not physical things. Blocks are abstractions.
Right. That's
So
what I mean.
So you'll have a block at the end that has an array of 8 sectors in it, because that's what a block is. That's what a block is. But you only have it mapped to physical storage of 1 sector. But I get what you're saying. Sectors are actual pieces of hardware. Blocks are not. Blocks are the idea of 8 sectors. So you will, in fact, have a final block on that hard drive in your example. A final block on your hard drive that thinks it controls 8 sectors, but actually only has physical access to 1 sector. Does that make sense? But realistically, you'd probably have it always be a multiple of 512, so that you had the, well, for the sectors, and then you probably also would have it be a multiple of, I don't know that a hard drive manufacturer would necessarily, to your point, what would probably happen is when you formatted the hard drive with a block-based file system, it would probably just omit that final block. So you would not have a block data type that would be mostly empty. Instead, you just have you'd have access to 7 less sectors than your hard drive actually, well, 1 less sector than your hard drive actually had. It would just pretend like that was unusable space. I think that's the way it would be handled. All right, so inside of my Gen hard drive, for my temp.sectors value, this is my pointer that goes to my collection of sectors. I'm gonna allocate some memory. How much memory? I'm going to allocate, did I include standard lib? Oh, I didn't yet. So standard library has the Malloc function. Malloc function has me type in a number of bytes in terms of size, which is going to be my bytes. Let's see, so I can say bytes, or I can say total sectors times 512. So the total bytes of memory that I want will be the number of bytes here, even though I'm going to think about them in terms of sectors. Since I'm going to abstract this and think of my hard drive as a collection of sectors, because these guys are a little bit more involved, it's not just a byte. This is actually, my hard drive is actually going to be a collection of sector structs. So we're actually going to say temp.total sectors times size of struct sector. So this guy is going to have a size associated with it. And our struct sector, this guy right here, he's going to have a size. It's going to be 32 bits plus 512 bytes. So this is going to be 516 bytes. That's the size of a sector, right? Because a sector struct has to hold 4 bytes and then another 512 bytes. That's what he holds. Realistically, since this will end up being a pointer, it'll probably come back with a struct size is going to be 4 and 4. So this will be 8 bytes big. It would be interesting to see what it thinks that guy is. Let's, why don't we take a look? Size of sector struct is size of struct sector. Yeah, I think it's going to hold, it holds a pointer and an int, so I think this is going to be 8 bytes. Oh. No, that's fine. Oh, it is 516. So it's giving it its full size of the memory. Well, actually, that makes sense, because when it actually creates memory for the struct, it's going to create enough memory to house the entirety of the struct. It's 512 byte array plus its 4 byte int. So 516. That makes sense. All right, so generating a hard drive, I'm going to allocate some memory. How much memory? I want enough memory to hold this many sectors times the size of each sector. because what I'm going to fill up that array with is an array of sector objects. That makes sense? I'm not filling it up with an array of bytes. I'm filling it up with an array of, like, call them objects. I'm going to fill up with an array of sector structs, which modern programmers can kind of think about like objects. All right, so that's what our hard drive will be. So if we say generate so the HDD will be gen HDD, and this guy takes in a number of bytes. So why don't we create a 1 gigabyte hard drive? So this is going to be 1 times 1024 kilobytes times 1024. So this is 1 times 1024 megabytes times 1024 kilobytes times 1024 bytes. All right, and then we'll go ahead and print out num sectors is going to be the HDD dot total sectors. And then we say and address, whatever. We'll just say %p. That's our pointer. And this guy will be the HDD dot sectors. That'll give us the memory address, which is the base address of our however many sector array that we have.
You need to return temp still.
Oh, thank you. All right, so we have, there's our 2 million plus sectors for a 1 gigabyte hard drive, and our array of structs will begin there. We don't have any structs in there yet, so we actually need to probably fill that up with some structs. That's part of what our hard drive does. If you go to the store and you buy a hard drive, it already has sectors in it, right? you got you some sectors. All right, so we're going to go ahead and fill that guy up with some sectors. So that's part of our gen hard drive. So now let's see, fill with sectors. So we're going to say for int I is equal to 0, I is less than temp.total sectors, I plus temp.sectors at bucket I think I should be able to address it like that, is equal to gen sector. So I'll generate a new sector and put it in there. So this will go through and get me my 1 million sectors in our current example, and just fill up that array with 1 million sectors. See how it took a little bit of time? You actually felt the time because I had to go and create all those instances of sectors. Okay, awesome. So now we have our hard drive, and if we want to prove that that worked, we can say %d here, and we can say sectors at bucket 14 dot, I don't know, here, we'll say dot bytes. So we'll put in that pointer. That's going to be the base address of the byte array of the sector that lives at bucket 14. So that guy. And if you want to see the amazing 0, you can put out byte count there and change this to %d, and now you'll get the byte count for that sector, which defaults to 0. Oh, defaults to 13 because I changed my gen sector code, right? So that was a good reminder for us since we changed all of our sectors come filled with some mystery. Somebody just try to talk? It sounded like Luke's voice to me. All right, so.
Nah, I've been.
It sounded like a robot to me. Does everybody else hear that too? Did you hear the robot sound with like the backsplash, or maybe it was feedback on my own mic? I don't know. Okay, so we kind of get what's going on here now? All right, isn't C fun? You really feel like you're kind of like working, like massaging the bytes. Really think about that in a creepy way, Eric. That's recorded. All right. Okay, so we have now gone up, and when we generate our hard drive, we actually build the hard drive, and we go ahead and install our sectors. That's what's happening right there. Okay, so now that I have that piece, now I need to be able to take we need to be able to store some things into a hard drive, right? And when we store things into a hard drive, what are we actually storing? We're storing blocks. So when we format a hard drive, so now we have to think about how do we create this abstraction. When I format this hard drive with something that's a file allocation table based formatting, I'm going to have a struct with an abstraction that sits on top of it. This is my hard drive struct currently, right? That's what that guy is. In order to blockify that, I need to create another struct, maybe called like formatted hard drive. Something like that, where a formatted hard drive holds a hard drive as well as an abstraction that lives above it that is the actual block representation of that hard drive, which goes through and generates blocks from every 8 sectors on the hard drive. I already have a hard drive with a bunch of sectors. Now I need when I format that hard drive, I'm going to be left with an abstraction layer of blocks. So to generate a block, I'm going to pass it 8 sectors, right? So let's go ahead and write our constructor for a block. This guy will be struct block gen block. Now to generate a block, I need to give it the sectors associated with that block, okay? And the sectors associated with a block are going to be places that already live in memory, right? So I need to give it the base address of the first sector. Does that make sense? So we're going to call this guy a struct sector pointer base address of call it sector group of 8. We're just being really verbose with our variable names. So when I generate a block, I'm going to tell it, here is the base address of the portion of the array of sectors that the hard drive has. You get from that guy forward 8. So you're that guy, the next 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 guy, and the next guy. I think that was enough, something close to that. Those are the groups you get because you get 8 of those. Okay? So we're going to go ahead and create our struct block temp. temp.use sectors will start off as 0. And then temp.sectors, notice this guy is a array of 8 sectors, or yeah, an array of 8 sectors, will be equal to the base address of sectors. Oh, is it not going to let me do that? Doesn't let me do that because of this. So I'm going to make this guy a sector pointer called sectors. And let's put a little comment. This is the base address of the first sector. Something like that. That's what a block will hold. Because if I had it with an array of 8, this guy is not something I could overwrite. He already gets his memory address. So now I'm setting his memory address to this base address. So if I go back to my picture here to see what I'm doing, this block right here will have his sectors starting right here, that base address. This block right here will have his sectors starting at this base address. And he gets the next 8. This guy started here and he got the next 8 for him. Okay, so I'm not creating new sectors. I'm just organizing the sectors that already exist into blocks. I'm telling each of my blocks where his place in the world is. You know, this is where you start and you end 8 bytes later, 8 sectors later, 8 times size of struct sector later. That's the real estate that this block governs. Okay, so that's our gen block. Well, almost our gen block. So this guy is going to set his base address, and then we'll go ahead and return temp. Yep. All right, so this will generate a block, setting the U sectors to nothing, and then setting the sectors to the next group of values. All right, so now when we have our thing for formatting our hard drive, so struct format HDD. Actually, I need to build the struct first. Hold on. So we'll create another struct up here. So struct formatted hard drive is going to have a number of blocks. So we'll actually programmatically answer Appel's question from earlier. You know, will be our implementation of the formatted thing, and we'll only include the full blocks that we can have. So number of blocks, and then we're going to have our struct block pointer called blocks. The base address of our collection of blocks that abstract an existing collection of sectors. That's what blocks will be there. We're not generating new sectors. We're subdividing the existing sectors into blocks, and then calling this guy, giving us a way of holding it called a formatted hard drive. Okay, so we'll come down here, and now we'll create something that's going to return a struct formatted HDD called format HDD, and he'll take a struct HDD in as a parameter. And his job is to format that dude. Strict. So I called it formatted HDD. Oh, I think it's probably because I haven't returned anything yet. So I'll go ahead and create a struct formatted HDD, call that guy temp. The number of blocks this guy is going to have, here I'll return temp here at the end. Why are you sad? Unnamed prototyped parameters not allowed. Did I not call it a? We're good. I can't refer to it that way. I have to do this.
You think it would let you if you like made it a pointer there, or
Well, I don't want it to be a pointer. do I? Struct HTTP. Oh, I need to give it a variable name. that's what it's expecting. This is a type right here. I haven't given it a variable name yet. Let me take this piece off. We'll call this guy the hard drive. There we go. All right, so he's going to take in a struct HDD, and we're going to go ahead and now I think you're actually going to be onto something with the pointer stuff here. And I think we're going to be okay since we're returning the actual struct. But remember, structs are passed by value, not passed by address. So any changes we made to this guy would not be permanent, but we're not changing him. We're just using his structure to tell us what to do with this new guy. Okay, so we're going to say temp dot number of blocks that we have here is going to be equal to the HDD dot total sectors divided by 8, right? Because we have 8 sectors per block. So our number of blocks will be that. All right, and then for our formatted hard drive, we're going to need an array of blocks. So what do we need? We need enough block structs to hold number of blocks. So we'll say temp dot blocks is equal to malloc temp dot number of blocks times size of struct block. So I need this many of these guys, and I need that total number of bytes is what I need to allocate. And then I'll go ahead and return that guy. But at this point, I still need to go through and I need to fill that array up, that formatted hard drive. I haven't formatted yet. I've kind of set up for the format, right? Okay, so now we're kind of thinking about how does formatting work? You know, I've kind of said, okay, well, so at the end of the day, this is kind of our file system, right? We haven't written how we use the file system yet, but this is the representation of our file system in terms of a collection of blocks that we're going to address somehow, a la file allocation table. Okay. So we'll go ahead and we're going to say, we're going to go through all of our blocks. So for int I is equal to 0, I is less than temp dot number of blocks, I plus plus. Now, I already have sectors. Okay, I already have sectors. This is the number of blocks that I'm going through. Here's my total number of sectors that I'm going to go through. So the number of sectors that are actually in the hard drive is this guy times 8. So I need to walk through my base sector by 8s. So int pos of base, let's call it pos of next base sector is equal to 0. So what I'm going to do now is I'm going to put temp temp blocks at bucket I is going to be equal to, I want to generate a block. And gen block requires me to give it what? I have to give it the base address of the sector. And the base address of that sector will be the HDD sectors at bucket pos of next base sector. This guy is an array of sectors. The thing that lives at bucket pos of next base sector is the sector that's at that bucket, which is an address. So he is a actual sector pointer. So we're going to give him the address of that guy. So this is going to be the actual sector from that guy. This is the address of that sector that will be pointed to by bucket I of blocks. And then what we need to remember to do here is plus equals 8. I walk through my collection of sectors by steps of 8. Those are block size steps. That makes sense? I can also, if I want to be generic about it, I can say, well, in the way we have it implemented right now, I need to say 8. I could be generic if I implemented it a little differently, but we've decided that our blocks are always 8 sectors. So my very first block will be the address of the sector at bucket 0. The next block will be the address of the sector at bucket 8. The next block will be the address of the sector at bucket 16. The next block will be the address of the sector at bucket 24. 8 sector hops through my array of sectors. I'm not creating new sectors. I'm just marking off my blocks every 8 sectors, keeping track of where the base address of that sector lives. That makes sense? All right, so what does this do? This effectively formats our hard drive. We haven't changed the sectors. All we've done is created blocks that this particular formatted hard drive will keep track of. And those blocks mark the beginning points of the various sector, what I refer to as clusters, that are on our hard drive. So what we just did is we created this array. We did not recreate these sectors. They already exist in the hard drive. All we did is say this guy points to the beginning of this sector, this group of sectors. This guy points to the beginning of this group of sectors, so on and so forth. The value this guy holds is the same address as where this guy lives. We don't have 2 different values. They both point to the same place. All right, any questions so far? Things are probably starting to get a little bit complex. Have I lost anybody yet? Go ahead, Blaine.
Is there a, I mean, it doesn't really matter because it's the same thing, but is there a demonstration reason for having positive next space sector and then adding 8 compared to just multiplying 8 to I in its place?
They give you the same number. I purposely picked a very verbose variable name to let us know this is the base of the next cluster, the next grouping of sectors. But you're right, the value will be the same. Okay, so that will produce our formatted hard drive, which is a block-based hard drive. So now I should be able to say struct formatted HDD. We'll call this guy the volume is equal to format HDD, the HDD. And then I should be able to say num blocks is %d. That's going to be the volume dot number of blocks. Here, let me just print that out first. Make sure that we're dealing with we're not zigging and zagging. All right, so number of blocks is 262,144. I think that's right. So if we have, how many? Oh, Ninja. Okay, so there's that divided by 512 is the number of sectors, divided by 8 is our number of blocks, 262,144. So that was our number. Nailed it. All right. Now, if you want to kind of prove our dividing up stuff a little bit, we should be able to say, let's see, sector 24 is going to be a pointer. And then we should be able to say something like formatted block, let's see, 0, 8, 16, 24. So it'll be bucket 3, %P. So this will be the HDD dot sectors at bucket 24. And this will be the volume dot blocks at bucket 3. Those should be the same values. So the third block, bucket 4, so our fourth total block, should have a base address that is equal to the sector that lives at bucket 24. Because 0 through 7 is sector 1, or block 1, or block 0. 8 through 15 is block 1. 16 through 23 is block 2. And then 24 through 31 is the fourth block, the block that lives at bucket 3. So those guys should have the same memory address. Oh, that's fine. Sector Formatted. What did this guy give me? Oh, because that's an actual sector, not an address. One moment. What's interesting there is look how we got the right value here, but then this guy became nil in the second one. but why? Oh, there's a hold on. I think it wants me to give it the. This is the address of what's here. This is the value of what's there, which is an address. That's going to be the struct. Yeah. Doesn't want struct. It wants the. That's just our wording. It's very interesting. Why does this guy block 3? And I did use the formatted thing, and I did format, right? Format hard drive, the HDD gives me the volume. And I did say the volume blocks 3. What does the volume do? This goes through and it sets temps blocks at bucket I equal to gen block, passing it the address of a sector. Oh, hold on. Well, no, that's right. Because a block is a number of used sectors, and the pointer to our sector so this will give me a block. I'm going to store a physical block here. That physical block will point to this sector. I'll add 8 to it over and over and over again, ultimately returning temp from our formatted hard drive. This is the volume, format hard drive, passing at HDD. Just switch back here real quick, because this is when it did show me both values, right? Or show me the second value being accurate. That's interesting. So then maybe this guy needs to be a percent. Is it a percent and? Is that another thing? Maybe it's a percent. That should be for a memory address. This should be for a value, which is a memory address. So if I say the sectors here, that should be an address. Let's just make sure I get two things pointed out that I believe should be there. Why does the second guy disappear? It's amazing. The volume at blocks 3 . So this is the address of that sector. That's correct for this pointer. And then our formatted block 3 is this pointer, which should just be the value that lives at bucket 3 of blocks, where blocks for this volume was allocated to be our number of blocks times the size of a block struct. That's enough memory. What I put at bucket 0, 1, 2, and 3. So I said temp blocks at bucket I gets generate a block, passing it the address of the sector. Gen block takes in a pointer to the base address, creates a new block, sets the U sectors of that block to 0, sets the sectors equal to that base address, then returns the block. What do I do with that block? I store it inside of temp at bucket, well, temp dot blocks at bucket I. Yeah, I think it's working, but why am I having trouble displaying this? I mean, the values are clearly stored correctly in those two. If I just say formatted block 3, here, let's do it this way. And then I steal this. And then I say sector 24 is the address of HDD sectors at bucket 24. Oh, it's the HDD. It's still the same. It's the first guy that's nil. Oh. That's the block. I want the sectors at bucket 0, which is the base address. Actually, I just want the sectors, which is the base address, same as bucket 0. There we go. Okay, yeah, so it's right. I just wasn't here. I'll show you what I wasn't doing. I was getting the blocks at bucket 3, which is a block, not a pointer, and that's why we were getting the warning that I was ignoring. I actually want the base address of his sectors. That's where the first sector lives. And that happens to be, so the block at bucket 3, his sectors are looking at the same memory address as the sectors at bucket 24. That's why these two addresses are the same. This guy and this guy. So block 3 is the 4th total block, which starts at base address of sector 24. Okay, so logic was right. I was testing it wrong. Okay, so now I have a formatted hard drive. What are we doing on time? Okay, so I have a hard drive that's already been abstracted now into blocks. So I effectively have this guy now. Now what we're supposed to have is a file allocation table. Let me bring up a here. So here's our file allocation table. And if you remember, I think I showed you a video last time. Where's our, well, we can go off this.
The file allocation table format was originally used.
I'm just going to jump
when we think of a
forward to
linked
use his example.
In the table, I see that the next block is 3. Again, going back to the table.
Okay, so a file allocation table is going to keep track of what these are the blocks. All right, so if I'm currently looking at this, well, here. We're asking whether a particular block is busy. So if I am starting at block 1, the next block is -1. So that is the, means I'm at the end of that file. Because remember, file allocation table tells us where do files live inside of our blocks of our hard drive, of our formatted hard drive. All right, so let's use this one as an example. So if I am starting to read in a file, and it tells me that the base sector is 6, or the base block rather is 6. It's going to go here. It's going to say the next block of this file is 3. It's going to go here. It's going to say the next block of this file is 5. It's going to go here. It's going to say now we're at the end. This block might not be completely full, but that's where the file lives. Okay. That's going to be our file allocation table. So our file allocation table is going to maintain an array of block numbers as well as where the next block in a file lives. Okay, so that means a file itself needs to know where its base block is. So when I say, okay, I want to read file X into memory, it needs to know here. Let's just watch this again real quick. It's only 2 minutes.
Through many iterations, but the 2 key ideas have remained the same. The first is that each file is represented as a linked list of blocks. Normally, when we think of a linked list, we think of the links as being part of the nodes in the list. Maybe the last part of the block would give the ID of the next block. Here, however, the links in this list are represented in the file allocation table, which is indexed by block number. Giving the starting block number of a file, I can find the next block with a constant time access to the file allocation table. A special value, -1 in this example, indicates that a block is the last in the chain. This file allocation table also contains a bit to say whether a block is free or not. In this example, our file starts with block 2. Looking at the table, I see that the next block
All right,
is
so
6.
this whole thing presumes that a file itself knows where its first lives, where its first block lives. And then we follow the file allocation table to go down the rabbit hole. Okay, so what we need to do next now is we need to create a how do we represent a file? So a file can be a struct that has so we have a struct file. And there might already be in standard lib something called file, but I think it's an all caps, so we can create a lowercase one. That should be okay. So this guy we can say has a file name, but well, I don't think there's anything wrong with that. But for right now, we don't really need it to have a name. So a file is going to have a starting block, which is just going to be an int. And then we might be interested in the total size of the file as well, even though we don't necessarily use that with the file allocation table, but just giving it a little bit. So size of file is this guy. Okay, so we'll create a struct for our file. Go back in here. We'll have a struct called file. This guy will have an int starting block in file allocation table. And then we'll also have a size in bytes, something like that. So I think for the homework, I'd ask you to like read in the size of a file. All right, so we'll go ahead and we'll create a struct file get file. And this guy will ask the user, enter the size of a file. And then we're going to say int. Actually, we could do this. Struct file, the file, and we'll say scanf %d, the file dot size in bytes. And then we'll say the file dot starting block in fat, start off at -1, because this guy has not been stored in a file allocation table yet. He's just a empty file that knows how big he is. Realistically, we would read in the data as well. But for our simulation, we don't need to read in the data. We just need to know how big the fake data is for our simulation. All right. So if we wanted to read in a stream of zeros and ones, we certainly could, and then reconstruct them later on. That wouldn't be a problem. So we'll go ahead and get a file. So I'll say struct file, the file is equal to get file. And then we'll do a printf, making sure this is reading it in. So file size is %d. The file dot size in bytes. Misspelled printf. D expects argument of type int pointer, but argument. Oh, I'm reading it into the memory address. So for scanf, where's my scanf? Get file. Here's the address of the student. I'll tell it where in memory it should put my integer. It's the memory bucket set aside by size in bytes for this file struct. All right, so I'll put in 25,000, and there's my size is 0, so that's not right. I didn't return the file. Where were you on that one, Blaine? Didn't you tell me I didn't return temp earlier? Can't be my fault.
You only paid for one check.
Everybody's making cutbacks during this coronavirus thing. All right, there's my 25,000. So we read in the file, and just to explain that a little bit, if you were having issues with scanf for reading something in, I created my struct here. So when I create my struct, a place in memory is generated for me. That's, you know, if I create an integer, a place in memory is generated for me, but we don't have control over where it stores structs, it stores ints, it stores chars, it stores those things in memory somewhere. All right. So when I created my struct here called the file, a place in memory was created for me, including a storage location for my size in bytes. So when I read in my decimal number, that's what scanf does. So I'm saying, you know, enter the size of a file. I read it in as a decimal number. It wants to know where in memory do you want me to put this number I just read in. That's what the ampersand rather, the file that size in bytes is. And then I'm just hard coding my starting block in fat to -1 because at this point I have not placed him into a fat file system. Okay. So what is our next step? Well, our next step is we now need to blockify a file, right? A file is going to turn into a bunch of blocks, but when we block a file, that's happening in terms of putting it into a file allocation table. So a file allocation table for our hard drive. So when we think about our formatted hard drive here, this formatted hard drive, we scroll back up. I alluded to earlier that this is basically our drive with our file system on it. So right now, this guy is keeping track of the number of blocks, and it's keeping track of the actual blocks. But he also is going to maintain a file allocation table, right? We will ask the formatted hard drive to look up a particular file for us. So he's going to have a collection of files that live on that hard drive, or a file. All a file knows about is where he starts in memory. So that's what a file descriptor is. If we think about it in terms of like the Linux operating system, we have something called an FD, a file descriptor. That keeps track of usually file name, permissions, a couple of other things, as well as the starting block for it when it's actually stored. All right. So our formatted hard drive here is going to store an array of files, a collection of files. Now, how many files can a formatted hard drive hold? What's the maximum number of files that my hard drive can hold? Not that it will hold this maximum, but what is the theoretical maximum number of files that my hard drive can hold? Go ahead.
Number of blocks.
Number of blocks. Why is that?
That's the smallest size you have available in your hard drive you know about through the software.
Okay. So if every single file I ever tried to put on here was exactly 1 block big, whether it filled that block or not, the most individual files I can store in a hard drive is number of blocks files, right? Okay. So that means I'm going to need a struct file pointer called, I'm going to call this guy file, well, I'll call it files to stay consistent. Linux calls these guys file descriptors because it's not the file itself, it's the information about the file. Where can I find the file whose data you've actually stored on the hard drive? Somewhere, okay? In fact, that's built into the language, isn't it? We'll just call it files and move on with life. All right, where are we on time? Okay. So we have our files. Now, when we format our hard drive, we now need to also give ourselves enough memory in temp.files is equal to malloc temp.number of blocks times size of struct file. You know what I called it? Size of number of blocks. It ends here. You know what I called it? Struct file.
Dr. Lippman, you typed the size of with an O in capital.
Oh, thank you. Were we on that one, Blaine? Actually, that's really bad. If V beat you to the Blaine's like, you paid for what? Just what? All right, so size of struct file. So this is going to give me enough space to hold this many at a maximum file structs. But now I don't know actually how many are in there, right? I know that I physically have a certain number of blocks, and I'm also keeping track of my total number of blocks, but I don't have my used blocks set up yet. All right, so we have a couple of different things that we can do here. As we go through and we fill up our array with pointers to things, or fill them up with actual structs, we have to start considering, well, what happens when I actually go to store a file into my file allocation table, or store it onto my actual hard drive, and I'm actually going to store a piece of data associated with a file at some block inside of my hard drive. And associated with that, I'm going to have a file that I'll store somewhere here in files that will be my file descriptor. So my file descriptor is kind of like this guy. You know, it'll say, oh, your file starts at bucket 6, or bucket 2 rather. And bucket 2 says, okay, I'm going to read the first part of my bytes from this block, and then I'll go to block 6 to read the rest, some more bytes. Then I'll go to bucket 3 to read some more bytes. Then I'll go to bucket 5 to read some more bytes, and that guy tells me, you're done reading bytes. No more bytes to read. All right, so I need to keep track of, I know how many blocks that I currently have, but notice this file allocation table, he keeps track of the blocks in your hard drive. So right now I have a collection of blocks, and I have a collection of files. Now my file allocation table, which is going to live here inside of my formatted hard drive, he will be a struct in and of himself that will have a bunch of indices, as well as whether or not they're busy or not. So you go back to this picture, each bucket of the file allocation table keeps track of whether or not that particular block is currently used and where the next block is in terms of the number. So it keeps track of a 0 or a 1 for use or not use, and it keeps track of a next block. So this is a struct right here. It's a name value pair. So I have a name value pair associated with busy, and I have a name value pair associated with next. So if I just create that struct real quick, this will be a fat entry. This guy will have an int busy. We probably would make it a short or a char or something, but we'll have an int busy, and we'll have a it was next, right? Int next. That's what an entry is in my file, my fat file allocation table. Struct file allocation table will hold a collection of these guys, right? So he's going to hold a struct fat entry pointer called the let's call this guy file blocks. And maybe he also keeps track of int number of blocks, because you might want to ask the file allocation table directly how many blocks he's controlling, how many blocks is he managing. Okay, so the file allocation table is filled up with a bunch of fat entries. All right, where a fat entry keeps track of whether or not this block is currently used and which is the next block it links to for when we blockify files. All right, makes sense what we just did with all that? All right, so let me do something here. CSC450 spring 2020 file allocation table. Make it public, create. Get a net. Ninja. There we go. See, it helps when you say ninja beforehand, it like works. All right, so we're gonna copy what lives up here. git push to here. Oh. All right. Then we actually put our file allocation simulator right inside of our my 450 thing. So I'm actually going to move that guy up a level. Yeah, we'll just put them up here. That's fine. So now inside here, I should be able to do a GitHub push. Wrote it. So here's this guy. What class is this? 450. So there's our starting code for that guy. All right, so if you already did your homework following something very, very similar to this, that's fine. You could just resubmit it. Otherwise, update your existing implementation, which I'm guessing is in different states of doneness, but this is another assignment, to use the struct structure that I introduced today. Because I'm guessing most of you did not do it this way. You probably had a fairly hodgepodgey pointers to pointers, a pretty ghetto solution would be my guess. So update your solution from last time. What's this?
I used a struct, but it didn't turn out like that. I can tell you that much.
All right, so try to follow what I did here and finish the implementation. We'll finish it up. We're not that far from being done. Hopefully I've shown you enough here in this thing that what a file allocation table is actually just a collection of fat entries. So the only thing we're really missing is the blockify the file and fill the, to generate your file allocation table as part of your formatted drive. So that's gonna live on the formatted drive. So we're 90% there, but you might not see that unless you understood everything we did today. So go back through the code, make sure you understand what we did today. Oh, let me think about this. I'll set it up for being due on Friday. But I don't care if you turn it in by next week. Really, it would be beneficial to meet another time, but the next time we would meet is final exam, right? We only meet once per week. Well, I guess whatever. So the final exam will be similar to the midterm exam in that it'll be 10 questions all online. I'll probably have it up by definitely by the end of this week. It might be up or middle of this week. You need to do it in a single sitting. It is depending on what questions make it on there, I might give you the ability to use your notes. In fact, I probably will. I'll probably let you use your notes for it. But there'll be 10 questions, probably half programming, half other, how do file allocation tables, things like that work. So I might give you some examples and you have to give me the answer, that kind of stuff. But the pretty traditional Littman exam, you've all had it before. So questions about the final, I'll just make it due by the like midnight on Friday of finals week. So you could decide when you want to set aside the time to do it. I'll design it to take about an hour, but I'll probably put a 2-hour time limit on it, something like that. So it shouldn't be a time crunch, but you also can't sit there for a decade and and solve everything. It is individual work. Don't work in teams. Other than that, Questions, comments, concerns, bribes? All right. Well, I will see you when I see you. What's Blaine laughing at now?
My dad's listened, and he told me to ask that or say that I'll take a bribe from you.
Well, I might be interested in that if you had given me more than one fix.
That's fair. That's fair. I'll keep that in mind for next time.
All right. I'll see y'all later.